always be inverse tan. And it's ironic how often those two functions go together, often. It's funny because you'll see these in a lot of cases. Sometimes it might be an integration by parts problem, but you'll see log and inverse tan. It feels weird, but you'll see that. And I go back to this. In Calc 1, my third exam in Calc 1 is pretty much all integration. And it's problems that if you haven't been practicing, it's really difficult to distinguish. And I've already done that in this class. Okay, just remind you. Would you say at first glance it kind of looks like the same question?
I know.
At first glance. Tell me about the first one. The degree of my numerator is 1 less. So the numerator actually is the derivative of the denominator short of a scalar multiple.
Right.
Which means if I put a 4, let's see, what do I need? I need this to be a 4. I'm lazy. That's the answer. I don't have to do anything else. Why? Because the degree was 1 less and it was a scalar multiple. That's why I said in Calc 1 you had to look at it and know the type or you're dead in the water. Because otherwise these look like the exact same problem. Now, I always said the priority was look at the degrees if the degree is 1 less. That's the priority. Now look at the second one. Is the degree of the numerator 1 less?
No.
No. Then the next thing you're looking at is the denominator, and I see a sum of squares. In other words, that now becomes my u, and there's my du, which means now the second one is what form? Inverse tan. Oh my gosh, yeah. Does that feel familiar? That's kind of what we're doing today. So the point was, when the numerator's of degree 1 less, that makes us happy. Because even if it's not the derivative, I can always manipulate it to make it like the derivative by adding and subtracting the appropriate things. That makes my life easier because when I do that, the log's out of the way and what's left is probably of a simpler nature. See, when we're pulling these apart, isn't this an easier one now? Because it's just a simple inverse tan. I don't actually have to do anything other than complete the square to figure out what are the actual numbers. See, I can't tell you what the argument is right now. I can't tell you. I had to do this because the argument is x minus 4. And I need that guy because he shows up right here and here. Isn't this cool though? That it doesn't matter what the question is. So let's have some fun. Let's make up some terrible numbers. Terrible numbers most people think of, let's use things like prime numbers. Because you can't factor things when everything's prime. Do you agree?
Yeah.
So
7.
X squared. What do you want your first coefficient to be?
7.
Okay, 7x. Now, the last one has to exceed something. Last one's going to have to be bigger than what? Well, 3.5 squared. What's 3.5 squared?
12.25.
So the last one has to be at least 13 to make it to be a sum of squares. You want to go 13?
13.
Are we? Is it safe to say that is horrible? I agree, that's horrible. All right, numerator. We'll keep it as integer coefficients, just not friendly ones. You need a 2x plus 7, so what if we use an odd coefficient? I need something x.
5x.
5x, beautiful. That, by the way, is now most unfriendly. I need another number here. Plus or minus what?
11.
Minus 11? Okay. You guys have a mean streak running through you. I love it. Now, this is exactly the same as the problems we've been doing. Not a single number is going to be happy. You're going to see irrational numbers in your answer. You're going to see fractions. You're going to see just horrible creatures. I mean, this one it's borderline out of control. I don't know if I should let go of the leash yet, you know? The wild dog that you set forth. Okay? But we can do this. All right, so the first thing I'm going to do is the u sub, because I can't pull it apart unless I know exactly what number to add and subtract to the top. So this is my first step. Let u equal x squared plus 7x plus 13. Then what's the du I need?
2x plus 7.
2x plus 7 dx. I got a 5x, which means essentially I have 5 halves times that. Agreed? So what? I'll put I need 5 halves times 2x plus 7. How do I know? Because that's how I get the 5x part. So what constant do I need? Five halves times 7 is 5 times 7 is
35.
35. Okay. Do we agree that's what I need? Yikes. I need plus 35 over 2. 11 is 22 over 2.
Yes.
So I need minus 11 when I'm all, so minus 57 over 2? Is 35 over 2 minus 57 over 2 equal to negative 11? Just doing some arithmetic there. I'm pulling this apart.
Yes.
22 halves, yeah.
Yeah.
Okay, so here's what we got so far. We now have, my numerator is 5x plus 35 halves, because you guys are just mean. Oh my gosh, this is terrible. Which, by the way, I can write the answer in the next step. What am I left with? Put it in front. Okay, put it in front. So 1 over. Now we're going to have to complete the square. We'll do that in a moment. We'll do that off to the side because that might not be as easy as the other ones. Okay? Now, didn't we just say this is exactly 5 halves times what we need? So could I pull out the 5 halves and put 2x plus 7 instead? I think that would be a wise move personally. Double check that you agree. Do I now have exactly the derivative on top?
Yes.
Which means I can give you the answers the next step. And it'll be a 5 halves in front. It's only a coefficient. Now, I gotta do the complete the square. I don't love that one, but I know what to do. So let's do this. You picked odd numbers, which means I got fractions. Ugh. Ugh. All right, I have x squared plus 7x, and I put the plus 13 way the heck out of the way. All right, so remember what the first step is? What goes here?
3.5.
No, I don't. You speak in mixed numbers. It's impossible.
7 over 2.
By the way, this is not a joke. It's impossible to do any form of mathematics with a mixed number. You can't add them, multiply them, raise them to a power taker. You have to change it to the improper fraction before you can do anything.
7
So
over 2.
leave it at 7 over 2. So now what goes here?
49 over
49 over 4. And so I'm going to minus 49 over 4. What a great choice, guys. Okay, so now 13 minus 49 over 4 is exactly what?
3/4.
It's exactly 3/4, plus or minus?
Plus.
Should be a plus because it's got to be a sum of squares. Would you say that's a big yuck?
Yes.
I think yuck is perfectly valid here. So this is x plus 7 halves squared plus root 3 over 2 squared. Remember, I need a squared. Can I now tell you the second integral?
Unfortunately, yes.
Is it going to be pretty?
No.
Probably not. The part that's not pretty are the coefficients and the constants. So the first answer, I'll bring way over. The first answer is 5 halves natural log x squared plus 7x plus 13. We've already deemed that's a sum of squares, so we can do this. The second answer is going to be of the form inverse tan of what? Ooh.
X plus 7 halves.
It's going to be an x plus 7 halves.
Times.
Now, the final manipulation we'll hold off on for a moment.
Reciprocate.
So
2 over root 3.
2 over root 3. Big yikes. By the way, we can choose to leave it like that. You might even say, distributing might make my life, that's a personal choice. Goes in front. Well, the 2 over root 3 goes in front, but what else goes in front?
Times 57 over 2.
Ugh. 100.
Well, at least the 2's canceled. So I now have minus 57 over root 3, which actually can reduce. That reduces to what? 19 root 3?
Yeah.
I would actually, in this case, I would actually reduce it just because it's, we went from extremely ugly to just very ugly. You agree? Does it, by the way, is it life and death whether I reduce this or not? Is it, yeah, I'd rather write that than that, but yeah. That was horrible. That's the worst problem you're ever going to see, yet it was exactly the same technique from beginning to end. The numbers were less friendly because you guys chose odd coefficients all over the place. You didn't have no perfect squares. Could we still do it from beginning to end? Yeah, one of the key steps was something like this. That's my 3/4. I still have to recognize it's the square of what? When it's a 9 or a 16, right, or 64, that's easy. What if that's a 13 or a 7? Heck, what if that's a 2/3? That's still the square of what I need. So that's the worst it could possibly be, is I have to think about it. But the worst it could possibly be was really arithmetic. It wasn't calculus. Okay, everybody cool so far? On board? So does it really matter how the question is asked? Quadratic, lead coefficient of 1. What if it's not a lead coefficient of 1? Then I multiply top and bottom by the reciprocal of the lead coefficient. That's probably not even going to be a thing. That's not something I'm going to ask you. I'm just going to start with this because I want you to get the technique. If my numerator isn't exactly the derivative of the denominator, or at least a scalar multiple, then I can add and subtract a constant, not a variable. I can add and subtract a constant to make it exactly what I need. And in doing so and pulling the integrals apart, the first one's a natural log that I'm probably done in the next step, and the second one's going to be an inverse tan. I just have to complete the square. I love this. This is beautiful. Okay? It's a beautiful method. It's not, what I'm showing you, there's no textbook. There's no YouTube video. You're not going to find this method anywhere. You're going to find these questions. You're not going to find the how. That doesn't exist in any written manual.
So for that, like, first step when you're adding and subtracting just like regular numbers, you're adding or subtracting what gets it to be the derivative, and then you're taking away or adding.
Yeah, think of it this way. This is what I needed.
And then you're taking away.
I don't know what I'm supposed to add, but I know it's got to add up to -11. So I just, I say, okay, what do I need to, I need this difference to equal -11. So that's literally how I came up with that number.
And then the one that you separate that turns into the tangent is like, it's what's left, kind of?
Yeah, it's because what did we start this process with? We started this process with 1 over sum of squares. 1 over sum of squares is as easy an inverse tan. You don't have to do anything. If I gave you the sum of squares and I put a 1, you're done in the next step every time. You notice that's why I keep putting the coefficient in front. I don't want this to get in the way of what I'm doing. That's also why I pull the 5/2 out in front so it's not in the way. Whatever reason, our eyes zoom in on coefficients. The coefficient just means that's going to be multiplied by my final answer, but I'll never get my final answer if I'm staring at the coefficient. So I prefer to always just pull the coefficients out because it's easier if that's a 1, because that's what the inverse tan formula looks like. Now, this isn't the only version of this. Now, I'm going to show you a really tricky one. Okay, what if how about if I do something like this? This is still considered technically, remember I said your denominators are of quadratic form. Do I have a quadratic in my denominator under that root? Yeah, because there's an x squared. There is no formula that exists that looks anything like that. But then again, the problems we're doing, they don't look like what we started with. We tweaked them. Any suggestion on what I could do with that denominator? Forget the root for a moment. Just look at the polynomial.
Add an x.
Well, yes, I could, but then I've got a product under the root. I don't know if that's going to make it better or worse. I can't use partial fractions because it's not rational. The root kind of limits. If the root was not there, this is a straight up partial fractions decomposition. Piece of cake, you'd factor it. But I got a root there, so I don't want to factor it. Can I complete the square?
With a square root.
It is, no, the polynomial part.
Yeah.
Does look a little goofy. Well, in order to complete the square, don't I have to have a lead coefficient that's a positive 1? Okay, let's start with that. Let's complete the square on that. X squared minus 8x doesn't look that difficult, does it?
No.
Huh. X minus what?
4.
X minus 4, so what am I going to add?
16.
And therefore, what am I going to subtract?
16.
4 squared.
4 squared. I like that. I'll do 4 squared.
Oh, interesting.
Yes or no?
Yes.
That's what you just did. It's not possible to do this without completing the square, but once I complete the square, I'm hoping I recognize this. We have an integral formula that looks like this. This is not a trig sub. This is straight up from last semester. It is a
Inverse sine.
inverse sine. Beautiful. Does inverse sine get the 1 over a in front? No. Inverse secant, inverse tangent do. Inverse sine is the one that doesn't, which means it's the one we probably miss the most often because we want to put it there. If my u is x minus 4, then my du is 1 dx, so I don't actually have to perform the substitution. Can I write the final answer as the next thing?
Yeah.
Again, when I ask that question, you already know the answer is going to be yes, but you have to recognize you don't have to do anything. All the work here was completing the square. So what is the answer then? Well, it's going to be inverse sine. My argument is an x minus 4, but
1 over 4.
1/4. Now, I'm going to show you something. Okay? Anything in front?
No.
No. Would it be legal to just say 1/4 x minus 1? Would that be legal? Yeah. Would it be a good idea? What's the only way I can check my final answer? Through differentiation. And I think it would be easier to differentiate in this form. It does not matter. It never matters. But I think it might be easier to differentiate if you have the x minus 4, because now you're doing the squares and all that kind of stuff. So I would probably opt for that. That's correct. I think that might be easier because, again, if I had to check it, and also if I'm going to use it, I think I would rather have x minus 4. Then take 1/4 of that result after the fact. Because what if x minus 4 is a factor of 4? That kind of thing. Okay? This is kind of an odd one, isn't it? It's the same overall umbrella that we just did. It's things of quadratic form. But this one was a lot different because it was under a square root, but it was still a quadratic. Therefore, I still did the complete the square as the method. Now, what's interesting, if you think about baby algebra, you all learned how to complete the square. And you all learned how to complete the square the class before you learned the quadratic formula. I was there. I was watching you guys when you were kids. I was standing outside. You probably didn't see me. It was the class before the quadratic formula. You learned how to complete the square. Because once you learn how to complete the square, how do you derive the quadratic formula? By taking the general quadratic and completing the square. And then the quadratic formula falls into your lap. You can't do it without knowing it. But then you realize quadratic formula, most of the time, not 100%, but most of the time is just way faster. It's much more efficient. You don't use complete the square to solve quadratic equations. You can't do anything with conics without completing the square. You use it for inverse trig problems all the time. We've been doing it today. Were we solving any equations? No. Complete the square is a ridiculously common. I'll put it in a different way. I do use the quadratic formula occasionally in a math class. I haven't used it this semester, I probably won't, but I will have completed the square 50 times in this class. The farther you go in math, you're going to find you use that technique far more often because you're not using it to solve problems, you're using it to change problems into a more useful form like we've been doing today. So to complete the square, and I'm going to go backwards a little bit because most of you are pretty sharp because you guys are like firing out. But I also notice there are pockets of the room that are dead silent when I ask what to do next. Which means that there might be a little bit of lack of complete confidence. Assume A is any real number other than 0. What's this then?
X squared plus 2ax plus a squared.
So anything in this form we know is a perfect square. So if I have something x squared plus 6x, I don't even have any other numbers. I want to complete the square. I need to know what number to add to make it look like that form. The mistake a lot of people have is they're looking at this and trying to figure out what to add. Never try to figure out what to add. Figure out what your perfect square is going to be. Then you'll automatically know what to add. I can trial and error and keep adding until it factors. We're going the wrong direction. So this could only be x plus, now what goes here? Because the completed
3.
square, this number has to be exactly twice as big as that number. That's why I say you always take half of it. That's why that's got to be a 3, because when I square it, I double it. And then what must go here?
9.
The square of that number. Now, x squared plus 6x plus 9 is not equal to x squared plus 6x. But if I do that, it is. So x squared plus 6x is equal to this. How do I know? Multiply it back out again. But the thing was, you take half of this coefficient and then you square it. If I'm solving an equation, I'm adding the same quantity to both sides. If I'm manipulating an expression, there's no equation going on, I add and subtract the same thing on the same side because I want to say it's still equal. Now, my Calc 3 class, on day 1, we do things like finding the center of a sphere. Do you guys remember doing things, taking circles, you completed the square so you can find the center of the circle and the radius? That was a baby algebra technique. In Calc 3, we do stuff like that, but we do it with spheres because we're 3-dimensional. It involves completing the square 3 different times. None of which are complicated, but if I don't do it right all for the x, for the y, and for the z, I can't answer the question. So that's one of the very first things we do on day 1 because it comes up periodically, but it's also what we're using from day 1, and folks will say, oh, we're still doing that kind of math? Yeah, in my differential equations class, we've already completed the square a couple times to answer questions. It's an algebraic technique that is just really, really handy to always have in your back pocket, like the quadratic formula, like your ability to use synthetic division. Right? These are things that come up and it's just really useful. If I don't have them, it's not that I can't do the problem, but I'm probably going to have to work way harder than I want to. Okay? Let's go ahead and stop that. Max?